So although in the model that we just estimated, it looks perfectly fine to keep on adding explanatory variables, as the mean squared error decreases with the variables that we add to the model. Here we're going to see that actually we're overfitting. So although everything looks perfectly fine on the trained data set, it doesn't look so great on the test data. So first let's try get an idea of what the mean squared error looks like when we're looking at the test data. So I'm going to specify the regression size for a reason that will be clear in a second. And we start with our best model. So the regression size is going to be equal to set to 9. So we choose our top model with all variables included. So we're going to have here range, regression size. And here we're going to have this list using Keras, losses, mean squared error. So the thing that we're trying to predict now is not y from the trained set, but y from the test set. So this is data that the model actually hasn't seen before. But we still use model to predict. But now we predict with our test data, not with our trained data. Again, we use the NumPy method, so Matplotlib can actually handle these outcomes, and we do this for each of the models that we have in vector results, all the way up till regression size. So we close this bracket, we close that one, and then we close the one over there. So this is now what it looks like, our mean squared error. And as you can see, for our top models, the models that include most of the variables, these are literally off the chart. Yeah, so you should multiply, so these are around 5 times 10 to the power 7. Yeah, so this is a huge number. So actually that doesn't tell me an awful lot, so let's reduce the regression size and make the model a bit smaller. And now you can better see the pattern that's going on here. So 0 here is the model where we only use a constant and x. And then we get the mean squared error. So this mean squared error is actually tends to be larger than the one you get in your trained data, because the model is actually fully estimated to get the best result on your trained data. So it's likely to get a worse result on your test data. But if next to x we also include x squared, you can see that the mean squared error is actually going down. So that's correct. So if you would not include x squared, we would be underfitting our model, because x squared actually helps to reduce the mean squared error in our test data. And because we generated the data ourselves, we know that x squared is important and should be included. But now if you move one model further and include x to the power 3 as well, you can already see that our mean squared error, our predictions are suffering on the test data. So on the trained data, of course, the relationship between the mean squared error and the variables that we included was downward sloping. On the trained data, it's always true that if you include more variables, your mean squared error goes down. But on the test data, this is not the case. And the test data often gives you a clue of how many variables you should include as the one that's minimizing your mean squared error on your test data. So this picture would suggest that you should not stop at the simplest model, which only includes x. You should include x squared as well, but including higher terms is actually a bad idea, because your predictions starts to suffer. And to get an idea of how that works, why did prediction start to suffer? We're going to make some plots. So I'm going to have this range x is NumPy range, and here you have to try a bit to see what gives you reasonable outcomes. So I'm going for this one to start with, and then I'm going to create a new data frame called dfplot. So that's from pandas data frame. specify the dictionary. So the variable now is called x, and it's equal to range of x. And to save some time, I'm going to do some copy pasting from what we had before. So I'm going to copy all this. So we go down here, and I'm going to paste it here. And then we're going to say that this is data frame plot. And then also here with these variables, I do the same trick. So this is one of the advantages of emacs, that you can actually edit in columns. So now we have added the constant to our new data frame df plot. We added the variables x2, x3 all the way up till x9. Oops. So we do a scatter plot of first our training data. So we take the variable x and we do the variable y as well. And we specify a label which says this is train data. And now what we're going to do is we're going to actually show what the models are doing when they're trying to fit our train data. So there's going to be range of x. And then we're going to have vector results. And I'm first going to look at the fifth model. So count from the end, so -5. We're going to predict. And we're going to predict using our new data frame df plot. And the label is prediction model 5. I'm going to do that 2 times more. So this is going to be model subs, this is going to be model 6, and here we're going to be doing model 7. This is going to be -4, this is going to be -3. Oops. PLT legend, PLT show. So now we run the code and see whether we didn't make any mistakes. No, it seems to be working. So here these blue points are the training data. And the blue line is the simplest model that we're plotting here. So that's model 5, as you can see in the legend. And model 5 is not doing a very great job because there are these points down here and the points up here, which is not capturing at all. And model 6, the orange line, and model 7 try to do better. Yeah, so they try to both get the point over here, then they come back to get these points over here, then they go down again to get the point that we have here, and they go up again to get to this point. Yeah, so these models are trying sort of desperately to improve the fit by getting into weirder and weirder shapes. And to see why I call these shapes weird, we can actually copy this line. And now do the test data here as well. Oh, let's remove the legend to make it a bit easier to see what's going on. So these orange points that we now added, these are the test data. So what you can see now is what these lines here, so our models 6 and 7 are trying to do. They're trying to improve on properties of the blue data that actually are not generic for the data itself. Yeah, because when you look at the orange data, there are no points down here which are orange. So the models, once we start adding more and more variables, like x to the power 4, 5, and 6, these models try to capture properties of the training data that are actually not generic of the whole data set. And in particular, these properties are not there in the test data at all. So that explains why these higher order models, although they improve things for the training data, they're actually making things worse on the test data, because they're trying to capture properties that are special or idiosyncratic for the training data, and they're actually not there in our test data. So that is the reason why, if you just focus on the performance of your model in your training data, you will always see an improvement if you start adding variables. It will always reduce your mean squared error because I'm optimizing something and I'm introducing more variables over which I can optimize. And I could always ignore them if I wanted to. So in my train data, this is always going to be an improvement. But that's why it's important that you split your data into a train and a test set, so that you can actually see whether the properties that you're picking up in your train data are actually there, also in your test data. And so that the properties that you're picking up are actually generic for the data set as a whole, and not specific for the things that you have in your train data. So this result that if you keep on adding variables, the performance on your training data becomes better and better because it starts to pick up particular features of your trained data. This is called overfitting. And the way you prevent it is to use test data and see whether these properties are actually also there in the data set as a whole.